Hey everybody, this is a preliminary video to my actual installation video. I highly recommend taking the key points here and doing your preparatory work. Before you even begin this project, you need to know what you can do and what you cannot do. I'm making this video standalone because there's just so much involved and a lot of initial thought that should go into planning before you consider doing this yourself. You need to examine your personal situation and your goals to see if this will fall in line with your overall skill set, your setup, and your whole scenario. There are some general practices to look into as an overview guide before you make your final decision to install your EV charger. Here we go. First, you want to look at your electrical panel. Is it at least 200 amps? Is it 150? Is it 100? If it's 150 and you have a tiny place with very few appliances, maybe that will suffice. At least the 200 amp panel is the recommendation. You can look up the square footage of your house versus the total power draw and see what you may find as an average. For example, a house bigger than 2,000 square feet with an air conditioning and a heater should generally have a 200 amp panel. You also want to see what the panel is rated for. A 200 amp panel may be rated for 200 amps with the rest of the components, or 225 or something. You just don't want to overload that. So even if you took a 100 amp panel and swapped the lug lines and upgraded all the wiring, the main breaker, and added breakers, so it's all 200 amp, the base panel still will probably overload because the bus legs are built for 100 amps. Let's look at the calculations. Many of you will look at your breakers on your panel and attempt to add each amp rating of each breaker up to compare it to your total main breaker, which in this example is 200 amps. They will likely be significantly more. This method isn't accurate at all. So when homes are built, the total power draw is considered. They even weigh in on future installations and try to future-proof it a bit. Not everything is used at once. For instance, the heat and the air conditioning, those are two major components. And loads are rated around 80% per breaker, per circuit, and the total panel, which I'll explain further in a moment. With all the above mentioned, you must account for the 80% rule. It's more of a guideline, but it's great to follow. The 80% rule applies to continuous loads. A breaker is rated for 100% of non-continuous loads. You're not to use or install more than 80% of the given amperage on the breaker rating. For a 125 amp panel, 100 amps max would be 80%, and that's what should be calculated when it's installed. For example, if you have an oven that uses around 28 amps max when measured or rated, you'd still want to install a 35 or 40 amp breaker pending the correct wire gauge for the supply, which I'll discuss in a moment. You would assume 28 is less than 30, so you could install a 30 amp, but that's wrong. 28 amps would be 93% of a 30 amp breaker, so it's not safe. You don't want to push it over 80. Note that 28 would be 80% of a 35 amp breaker, and 32 amps would be 80% of a 40 amp breaker, which is safe. But the same concept goes for the total amperage use in the house to the panel. So 80% should ideally be the maximum load to the house at peak times. Therefore, a 200 amp panel shouldn't see more than 160 amps at peak times. This isn't always the case, but it is ideal. Albeit, you must consider the wire size. I'll discuss that in a moment. You cannot put a larger breaker. That will start a fire or melt the wiring if the wire is not correct. I stress this. If you think you're close, you may try to consider how much electricity you'll use. How many appliances are gas versus electric? How many big items do you have, such as pool pumps, ovens, washers, dryers, microwaves, garbage disposals, air conditioning units or multiple air conditioning units, water heaters. Those are huge ones if they're not gas. Water heaters are a huge draw. Dishwashers, etc. If you only charge once a week, it's possible that you can habitually not run these larger components and during your EV charge and possibly make it work. So the trade-offs can work if done habitually and considered. Another estimation would be to look at your highest electric bills, for instance, summer. Look at your peak kilowatts which are consumed. Now, there's a difference between kilowatts and kilowatt hours. So kilowatt measures power, the rate at which something uses electricity, whereas kilowatt hours measures the energy, the total amount of electricity used over time. You'll then calculate the amps and take that number divided by the current coming in, which is 240 volts for the US. But unfortunately, for Southern California Edison, they only provide kilowatt hours and not kilowatts, so we cannot calculate the peak. While this first calculation referenced is not really viable to use, I wanted to put it in the video because a lot of people may try to reference this for gauging what their panel can and cannot handle. A kilowatt is an instantaneous value. An amp is also an instantaneous value. The amp is what you're searching for because you want to see the peak value of the max load on your panel to see if it can sustain more capacity. A kilowatt hour is an interval over time. So that would be deduced into an amp hour, also an interval over time. Both of those are really not going to help you calculate instantaneous values that you need to see the max peak at any point in time and see if it's safe to add more power to your panel. The only viable way I see this working, and it's intricate, is to go to your monthly bill, look at the entire year, take the peak month, go into the month, look at the entire month, take the peak day, and then go into the day and take the peak hour. Maybe at this point you can try to assess what you were doing, what you were using. For most people, this will be summer and it will be air conditioning use, etc. Based on that, you can try to gauge what you were using, what the situation was, and try to replicate it. The solution to this issue is actually a really awesome device. It's made by Emporia, and on Amazon it's relatively affordable, far cheaper than the other loggers I've seen, which require separate software and subscriptions. Pick one of these up, install it, very simple. They just loop around the wires of each individual circuit and also the two main lines, and they even have flexible adapters if you don't have a lot of space. This will enable you to log by the second or whatever parameter you choose, export the data, possibly Excel sheets, and then filter it so you can find your peak. The best part is it runs off of Wi-Fi, so it just goes right to your phone and everything can be tracked without having to touch the panel again. You can also trace things through your house, or if you have an overloaded circuit, or you're worried something's a drain, a particular appliance in a particular room, or just your overall usage if you want to track it or maintain solar values, etc. This is an awesome tool. Link is in the description. You can calculate your usage, but without kilowatts, you cannot calculate a peak at all. What you want is the peak for the max draw so you can see if your panel can handle it. The closest you can get to accurate load max is the real-time function on your meter, or get a cheap amp meter, get the right one, and I'm actually gonna make a short video about that next week, so subscribe, or in the coming month, I should say. If you have the main breaker tripping, you can watch the peak kilowatts on the meter to see how much is being pushed at that time. You can also try turning on all the appliances in all the rooms and using the max amount that you would assume that you would use at once in your situation, and then look at the meter in real time. I did a calculation based on some research that I found, and it was relatively close to the draw that I was testing and getting. So I'm gonna explain this now. This is an estimate, so don't read too much into it, but it was kind of fun, and I did it for a few houses, so you can check it out. I've done some research to find calculations that are remotely relevant, and this is one that electricians use. There are several, but this is one that is known to assess fairly well. What this calculation is going to accomplish is the theoretical capacity of not only the circuits in your house, but the overall electrical service at the panel. Then we're going to compare the load and see if your panel is capable of upgrading or sustaining an EV charger outlet. I'm providing an example that I created so you have something tangible to follow along with. You're going to separate the circuits in your house. You're going to do the general lighting and outlets, and then you're going to do the appliances, and then you're going to do the HVAC. Most people will have their panel generally labeled with something. That should at least allow you to separate the appliances. A good way to go about this is just to turn off breakers one at a time, or turn them all off and turn on one at a time, and just have someone else on the other line on a phone and see what's turning on and what's off and try to trace it. Most likely walls and rooms will be quite close to each other, and bathrooms on a circuit and kitchens on a circuit and appliances in the kitchen on their own circuit, and etc. In each one of these sections, you're going to have to separate the amperage of each breaker and then the voltage going to each breaker. If you first look at general lighting and outlets, you notice there are two sections labeled by bullet points. The first section, they're all 20 amp. For default values, we're going to say that if it's not labeled, it's one pole, single pole. So these are all single pole 20 amp breakers, 3 of them. Right below that, there are 7 15 amp single pole breakers. This covers the entirety of the general lighting and outlets. Single pole breakers are 120 volts, 2 pole breakers are 240 volts. 2 pole breakers are easy to notice because they have a bridge going across the breaker. Let's look at a calculation. For the first one, you take the 3 breakers and you add them together. So the breakers are rated at 20 amps each. 3 of them makes 60 amps. You then take that 60 amps and you multiply it by 120 volts because these are each single pole breakers. Only 2 pole breakers are 240 volts. This amounts to the 7,200 watts, the maximum capacity of the breaker. However, due to the 80% rule, we don't actually use that much. So we're going to take that 7,200 watts and we're going to multiply it by 0.8. That gives us 5,760 watts. This is accounting for the 80% rule. Keep in mind that this doesn't mean the breaker actually reaches 80%. In fact, it probably hovers well below that majority of the time. Repeat the same calculations for the 15 amp section below. Once you've subtotaled the 20 amp section and the 15 amp section, go ahead and add those together. Here, I added these sections and I got 15,840 watts. That is the subtotal of this section, which we will use later. Now look at the appliances. There is a 30 amp dryer and a 30 amp pool pump in this section. These are separated because they are 240 volts when you multiply instead of 120 volts. This is because they are 2 pole breakers. Notice the 2 pole in the parentheses. If you do the math, you get 11,520 watts. Below that, in the subsection, you will see a 15 amp garbage disposal. It defaults to a single pole because it's not labeled 2 pole, and I did the calculations below, getting 1,440 watts. Just below that, you'll see 3 20 amp breakers for 3 more appliances, also defaulting to 120 volts because they're single pole. Do those same calculations, you get 5,760 watts. Now that the appliances section is broken into the parts and finished, you will go ahead and subtotal each section within it. So you take each bolded section and add those together, as you see below. 18,720 watts is the subtotal for this section. Lastly, we're looking at the HVAC system, which will be your heat and your air conditioning. You are only going to take the greatest value between these two because you never use these at the same time. Also note that you can choose this same sort of optimization in other sections if you know that you don't use 2 appliances at the same time. For the heater, we only have a 15 amp in this case because this is a gas furnace. If it were electric, it would probably be between 50 and 80 amps. Therefore, we're going to settle on the 50 amp breaker for the air conditioning, which is 2 pole. So if you look at the calculation, we're multiplying by 240 volts. With the calculations finished, this yields 9,600 watts. So the subtotal of this whole section is simply 9,600 watts. Now we're going to move on to the final calculations. Bring over the lighting and outlets subtotal, which is 15,840 watts in this example. Then bring over the appliances subtotal, which is 18,720 watts. Now you're going to combine those, which yields 34,560 watts. Now you're going to add in a formula, which is a little bit outside of this scope, but generally used, and just follow along and roll with it. Take that appliances, lighting, and outlet subtotal, which is 34,560, and subtract 10,000 from it. This gives you 24,560 watts. Take that number and multiply it by 0.4, making it 40%. So that is 9,824 watts. Now roll that number over and add back in the 10,000. This gives you 19,824 watts. You're almost done. For the final piece of the puzzle, you are going to add in the HVAC system. So we're going to take that air conditioning calculation, which was 9,600 watts, and we're going to add that into the previous number we just pulled from the formula, which was 19,824 watts. This totals 29,424 watts. You're going to take that number and divide by the total voltage of the house coming in from the street, which would be 240 volts for most US residents. And that gives us a grand total of 122.6 amps. Yay! What does this mean? Well, you're going to take that number and you're going to hope that it's somewhere around 80% or less of your main breaker or your panel rating. For example, this home is on a 150 amp panel. 122.6 amps is slightly over 80%, which would be 120 amps. Very close. So, and this is also a theoretical max for that 80%. So this is relatively safe and likely uses a lot less in most circumstances. If this exact home with this calculation was looking to install an EV charger, they might want to go against it because they're too close in the numbers and there's not a lot of room to play there. If you look below, you'll see an example of someone adding in a 40 amp breaker for their EV. If you take that breaker and you take 80% of it, that would be a 32 amp max load that breaker would be delivering. You take that 32 amps and you add it to your original 122.6 value that you got from all the calculations, then you would see you get 154.6 amps. You already know that's more than 150 amps, which is the max rating of your panel. Additionally, if you divide that, you see that it's 103.1%. Being that everything is supposed to be hovering around 80%, you're already 23.1% over with the EV charger. And again, the only way this would be sustainable is if you turned off all the appliances in your house and habitually charged your EV when this was the situation. Other than that, this isn't really safe to do and I would not recommend it. Let's look at a 200 amp panel example. Right now, as it stands, you have 61.3% capacity as is, so you do have some room to work before you hit that 80%, or at least hover around there for safety. In the example, again, I will use the 40 amp breaker for installing a new EV outlet. If you take 80% of that, again, it's 32 amps. You take that 32 amps, and again, you add it to the current output of the calculations you did, and you get the 154.6 amps again. In this case, you're going to divide that by 200 amps because that's the size of the larger panel, and then you get 77.3%. That still is not 80%, so you are in the clear. You are actually 2.7% below your panel's calculated capacity or safe capacity level. This puts you relatively close to that 80% capacity. You're safe to install a 40 amp, maybe even a 50 amp. You have to use your discretion when you're calculating these things and considering what you use and you don't use. Some may even hover around 90% or between 80 and 90, and at times that may be sustainable and fine. So again, you have to use your discretion. You want to generally fall within that 80%. So this is how you would calculate it and look at it and get a good estimation. This is just an estimation, but it is a fairly good one. If all that checks out, or if you want to attempt the installation and see what happens, and see if it would sustain, then you need to check out the physical space in the breaker box. Breakers. Tandem breakers are best friends. If you have large breakers, which I'll show, you can condense them from 2 breaker spaces down into 1, in a 1 breaker configuration, so to speak, aka a tandem breaker. You can play with the configurations and determine which you'll downsize and which you'll adapt together. It's all relative to your personal setup. Focus on the complex parts, the panel and the load. Let's say that you decide to condense 2 15 amp breakers into a tandem. You want to do a quad breaker, such as I did, or do separate tandem 15 and a tandem 50. You must understand if your panel can accept a physical breaker insertion on the bus bar. The bus bar is the line running down the breaker panel. The bar is actually 2 sides, or they're called legs. Each leg is on a separate phase. So 120 volts goes through each leg or phase. Older homes usually have solid stabs. Some homes have a mix of solid and notched stabs. Some have all notched. Only a notched stab can accept a tandem breaker. Remember that. If it's solid, you cannot condense to a tandem breaker. You may be able to shift around breakers to fit this one here and that one there if your box is half solid, half notched, as many are. If not, you'll have to install a new panel, a sub-panel, to accommodate what you need. What I'm referencing are called stabs. I'm going to show you here. Look at the 2 types of stabs. There's notched and there's solid. The reason they are different is for physical limitations in order to prevent overloading of panels. Circuit total limitation, CTL, is the US term for panel rules. Stabs are designed with notches for tandem in order to prevent circuit breaker overload in a panel that was not designed for it, or for someone to change every breaker in the panel and make them all tandem, theoretically doubling the power of the panel draw and overloading it, right? This is why you see that most panels are a mix. The panel cannot support more tandems than notches it has. Some panels are bypassing this, so I've heard, I don't know, but it's basically a physical limitation, so you'll want to pay attention to the stabs on your panel. You need to make sure that you use 2-pole breakers. They're connected by a bridge or a bar or whatever you want to term it. There are phases on each bus bar, each 120 volts, with one at phase 0 and the other one at 180 for split phase households, which is common in the US. You must have your 240 volt source, such as an EV charger, on separate phases. This is where a 2-pole automatically does it for you. If they were on separate breakers, it should theoretically yield 0 volts or cancel because they'd be on the same phase, but there are other repercussions that could happen, still may be live, damage stuff, just don't try it. Watch for the bridge that makes the connection across the double breakers if they're 240 volts. That's simple. If you swap breakers around, you could unbalance the load. Each bus leg is supposed to be balanced with the other. They should net zero when the power returns from the neutral. This can be adjusted by swapping breakers around. You could tediously test for each circuit and try to do this. Assuming you know what you use and you figure out which stuff is on which circuit, labeling your breaker box, and then looking at the amperage on the breaker should allow you to try to balance it fairly well with an approximation. Note that 2-pole breakers auto-balance, as I said earlier, because each pole is already on a separate phase. You must find and source your brand panel breakers as they are specifically meant for your panel. So each panel brand should have matching brand breakers. Do not get generic ones. Don't go on Amazon and find ones that look alike. They're not the same. Many brands in the past have bought out many other brands for decades. They keep overlapping. It's very hard to keep up with unless you're an electrician, right? But they usually offer a superseded version for the breaker you need, no matter how old it is, at least that I've found. I do recommend using AFCI, arc fault, or GFCI, ground fault breakers, especially if it's code. What these are 2 types of breakers that provide additional safety protocols over the standard overload types, which are probably in your panel. And they accomplish this in different ways. The AFCI breakers are for bedrooms, at least here in California. I believe that's code, and the GFCIs are for kitchens, bathrooms, outdoors, etc. No, you technically do not have to pay more for these very expensive breakers if you do not want to. I believe in most places everything is grandfathered in, so if your panel's old and it still works, you can just leave it as is, even if it's not up to code. However, if you can afford and source it, just do it. That is my recommendation. Definitely get those if you can. Now you've decided it's possible, what's the plan? Think about the charging requirements and how you'll actually use the outlet and what your needs are for the car and charging timelines. For example, I had the option of using 40 amp charging or 48 amp charging. I believe that's the max in residential right now. I chose 40 because the outcome of delivery, 9.6 kilowatts versus 11 kilowatts, is really negligible to me. That's maybe a 1 to 2 hour charging time difference from 0 to max. But in residential homes, it's still going to take hours, so what's the big deal? Let it charge overnight. The car wouldn't need charging daily, it wouldn't need instant charging, and the strain on the house is already tight with a 200 amp panel, so 40 amp charging was sufficient. What's next? Choose the location of the outlet. Look at where your panel is on your car for charging, try to measure up, try to measure over. If you have the ability to run it next to the breaker panel or right through the wall, great. For a 40 amp charger load, you will need a 50 amp outlet, 6 gauge wire, and a 50 amp breaker. Remember the 80% rule. Alternatively, if I wanted the 48 amp charging capacity, I would have needed a 60 amp outlet, a 60 amp breaker, and 4 gauge wiring. And the cost would have been nearly 3 times or more just for the parts. Think about how often you'll need to charge, where the charging port is, the length of the OEM charging cable, your ability to park, reverse if necessary, all those sort of scenarios. In this case, it was just too big of a car and too small of a space, requiring reversal in every few days. The few hundred extra to run the cable across the garage was worth it in the long run. So consider your future and your usage. The wiring size is very important because breakers are there to prevent wire damage, or fires, or device damage downstream. That is the purpose of breakers. The wire is the key part. The breaker is dependent on wire size. It cannot go above the rated wire size, but it could technically go below on some houses. For example, some houses may have 12 gauge wire all around for basic 15 amp breakers, which only technically require 14 gauge. Note that wire gauging is reversed. It's not intuitive. So the larger the number, the smaller the wire. So at 0 gauge, which is the largest, they start going backwards. For a 200 amp panel, you'd need a 3/0, which is essentially a 000, or you could think of it as a -3, though that is not actually correct, but you get the point. The lower the number, the bigger it gets. In this project, a 6 gauge wire is the minimum standard for the 50 amp breaker that I required. 4 gauge wiring for the 60 was the alternative. You definitely want to use copper wire only. Use the right gauge, I already said this, but aluminum is not recommended. And if you happen to use aluminum, I know places still do, it's usually a step lower for the same power. Don't quote me on this, but I believe I've heard that. So A 4-gauge aluminum may be required for this job for the same 50 amp breaker, whereas I'm using 6-gauge copper. Aluminum just is not a good conductor, not compared to copper, and it loses energy in particle collision and heat loss as opposed to copper, but that's beyond. It's just not ideal here. The different types of gauges of wire have max distances. For THHN 6 here, it was 100 to 150 feet, I believe. I only used about 40 feet to cross the span of a double garage, but you must account for that if you're running extreme distances, so do your homework. Wiring is also the expensive part if you're running long distances. I paid about $60 per roll, and I needed 4 rolls, 50 feet each. You'll need 4 wires. You'll want to keep the wiring the same as the standard residential wiring, which is green, white, black, red, and we'll discuss that. That's also in the installation video. The NEMA 1450R, R is for receptacle or female, is the right plug for this particular job, and most others in the EV setup, as far as I know. You must match your vehicle's plug type to the correct outlet. So if this isn't it, you want an adapter. So you want to check what you have. The BMW 2023 iX that I'm using as an example comes with the 1450P, P for plug or male, and that's an adapter to the charger box. We use the OEM charger to save $500 to $1,000 because we don't really need the kit. Unless you use your OEM charger daily, just save money and use that for the wall. But the OEM one is good as long as you don't plug it in and unplug it often. One thing to note is these outlets are not meant for daily use like your typical house outlets. You should leave it plugged in and not take it in and out as you'll loosen the internals over time. They are not the same. The fun part, running the wire. Conduit is what you want to think of next. I chose THHN, and that means I can run it inside of Conduit. You do have many options here with the wiring and running it, and it's up to you. Different locations will have different codes and laws, and no, not everyone follows them, not even electricians, but keep this in mind. You could potentially save money by running a 6.3 Romex as long as it's in a finished wall and up to codes, such as you may need to drill holes several inches above in 2x4s and run it. It's a lot of tedious work. It's cheaper, but as the walls here were all finished, and for safety reasons, I chose Conduit because the future homeowners may puncture something through the wall and hit a line and not know it. Side note is that AFCI breakers usually sense things like this. You cannot run Romex in Conduit. It's basically sheathed inside of sheathing, and the heat dissipation, among other things, is just not safe. So don't try to do that either. Definitely do your homework on Conduit and running wire. So electrical conduit is not the same thing as PVC for your sprinklers. Schedule is referring to the pipe wall thickness, and Schedule 40 is normal. Schedule 80 is thicker walled with less room inside for wires. You can reference the tables here and see the max size and number of wires that can run through the diameter of piping. Each gauge wire is different in fitment inside the specific diameter piping. So the smaller the diameter of the piping, the more money you'll save on it. In the chart, you can see that 3/4 inch Schedule 40 was ideal for 4 6-gauge wires. If you're doing great distances or mini bends, maybe bump it up by 1/4 inch just to have slightly more room to work with. Especially if you're doing Schedule 80, that is thick stuff and will cut it down significantly. I would probably use Schedule 80 if it's outdoors, but local laws may require all metal conduit for outdoors. This was in a garage, so Schedule 40 was fine. There is a chart for metal conduit. I'll put that here. You can also get wire types that are able to be buried in the ground and not need conduit. Most of us DIYers will probably just run conduit. Use metal outside and always make sure to properly water seal all your conduit types with glue and fittings or whatever else you need. I will mention safety. Again, do this at your own risk, okay? That is fair warning. When you're working, you will have 2 lugs that power the panel from the street transformer. These will always be live, 120 volts each lug, and usually the plate that spans them. You will want to steer clear of these always. Even if you shut off the main breaker, these are live. I had to work very close to these, but I was quite careful. Some places require calling in the city to turn off the power to the main breaker. Some you can pop out the meter and disconnect 2 sections to disconnect the main breaker, and some have another service panel shut off, etc. It is best to shut off the power to the main breaker if you can, but it may not always be possible. Turning off the main only turns off the bus bar. Still, the voltage fed into the lines will be live from the street. I keep emphasizing that, so remember. Some safety items. Wear rubber gloves that are insulated, and not the pullover latex gloves, but try to get real rubber gloves. I can put a link in the description. Work with one hand at a time when you're in the box, if you can. If you grab with two, it's more likely that you'll close the circuit and electricity may flow through you, where otherwise it may divert partially or fully if it's just one hand. Use rubber shoes or a rubber mat if you want to be extra cautious or have those. All of that stuff will just keep you safe to a degree, but you must be aware of what you're doing all the time. I just want to emphasize that again. Always test for live power before touching anything. Even though I know something is not live because I've done it so many times in one place, I will still pull out a multimeter and touch the leads to make sure it's off. So just do the same thing. Okay, so you attempted it all, you installed it, you tried to calculate, and you misstepped. Worst case scenario is you begin to throw the main breaker or even the charger breaker when the circuit is overloaded. In this case, you can't use it unless you possibly use nothing else. What you want to do is leave your work, turn off the breaker, and call an electrician. You may have to upgrade the panel, or they may provide some other option. Nothing will be a total loss. Most electricians I've met are fairly cool. They usually cut corners as normal humans would, if it's still safe. They may conserve most of your work and expand on it. The budget here was roughly $700. I calculated it in an Excel spreadsheet, but it fell slightly under. I did have some tools already, which many of you may not have. I'm going to put a list with all the links of everything I compiled and researched and needed below. Theoretically, this is all easy to do. It's just time consuming. Hopefully this video has addressed some of the questions and thoughts around all of this. Each project will be different. I even made a calculated project template on Excel and automated the cost and used graphs and all the fun stuff. I realize that's overkill. I recommend penciling out what you're going to do in your plan in writing. That always helps. Collect the parts beforehand, be organized, prepare well, pre-plan, and then roll with the punches along the way. No matter how prepared you are, you still may have to adapt and buy something or go through something you did not foresee initially. I am going to do a video on electrical panel basics, just things that I've picked up over the years. In the next few weeks, I'll put that up. That should help assist on the fundamentals even more so with understanding what you're doing. Everything here is a compilation of things I've learned over the years. I am not a licensed electrician, and truly you do not have to be a professional to do many of these things yourself. And don't tell them I said that. This is one of the things you can do yourself. If it gets too deep or you feel stuck or constricted, then it's time to call an electrician. There's no shame in that. Do your best effort, especially if you're mechanically inclined or an engineer or something along those lines. I just wanted to go off on a tangent here and thank all my subscribers. You are all awesome. I especially appreciate the ones with the kind comments. I consistently bring up the rare level of kindness I've received on some of these comments as opposed to the typical YouTube impatience. So thank you. The positive outlook on life is awesome, and I love to see that YouTubers are sharing goodwill. Anyhow, this should help you evaluate your situation. Watch the installation video for a hands-on approach as an example, and make sure you contemplate your circumstances before you begin. Plan well. You can do it. Thanks for watching. I will see you all in the next video. Take care.